Hey PStat, continuing section 5.3. So this is really one of my favorite tools for dealing with some more complex problems when we have conditional probabilities and events kind of lined up in a row and things like that. So a tree diagram shows the sample space of a chance process involving multiple stages. The probability of each outcome is shown on the corresponding branch of the tree, and all probabilities after the first stage are conditional probabilities. So, for example, we've got a tree diagram here displaying the sample space of randomly choosing a school day and noting if Shannon hits the snooze button or not. And whatever she gets, whether she gets to her class on time. All right, so we have initially a 6, and so what we do is we have we call it a tree diagram. Kind of look, I don't know, it branches out, right, and it doesn't usually branch back together. It splits up. So at the beginning of this process, she either hits the snooze button or doesn't. All right, and so those are the two possible outcomes in kind of the sample space of that little chance process, right? What we label on the branches of the tree are the probabilities. There's a 60% chance that she hits the snooze button. There's a 40% chance she doesn't hit the snooze button, kind of heads down these paths. And notice that whenever you do a split, it adds up to 1. Then, if she hits the snooze button, these are conditional probabilities now. And that's what's really nice about the tree diagram as opposed to like a Venn diagram or a two-way table. Like we can actually label it with conditional probabilities. So any problem that deals with conditional probabilities, the tree diagram is going to be, probably your choice. And generally those are going to be the most complex ones. So in a lot of ways, this will be the most useful tool we have. So the probability that she is on time, given that she hit the snooze button, is 70%. And so then that's a 30% chance he's late. Notice those add up to 1. Notice that down here, we also have another on time, right? So this is kind of like the same outcome, but it's given this other conditional. Notice she's 90% chance of being on time if she doesn't hit the snooze button, which makes sense, right? If you snooze more, you're more likely to be on time. Or sorry, if you wake up earlier, you're more likely to be on time. So we have here, the fact that these two numbers are different shows that these are conditional probabilities. It also shows it's not independent. If it were independent, these would be the same. This pair of numbers and this pair of numbers. Since they're different, we know it's dependent. And so that can be very useful for modeling some complex problems with conditional probabilities. For example, recently Harris Interactive reported that 20% of millennials, 25% of Gen Xers, and 21% of baby boomers and 70% of matures, so age 68 and older, read more ebooks than print books. According to the U.S. Census Bureau, 34% of those 18 and over are millennials, 22% are Gen Xers, 30% are baby boomers, and 14% are matures. Suppose we select a U.S. adult at random and record which generation the person is from and whether he or she reads more ebooks than print books. So, draw a tree diagram to model this chance process. This can get very complex, so very quickly. So first, we're going to split off with the percent that are in each of these categories. So 20% millennials and so on and so forth. And so, or let me, maybe I actually got this backwards. Oh yeah, sorry, I was wrong on that. So that's actually of the millennials. 20% of the millennials read ebooks. So that's actually, we're going to split off first. We're going to split off this first. And we're just dealing with our population over 18. We have 34% millennials and so on and so forth. Of that 34%, 20% read ebooks. So let's look at this here. This is the whole chart kind of laid out for us. So of a randomly chosen adult, 34% were millennials, and this is over age 18, 22% Gen Xers, and so on. And so 22%, 30% there, and 14%. That's our different groups. Then, given that they were millennial, 20% reported that they were more likely to use ebooks. And then of the Gen Xers, it's 25%, and then 21%, and so on. So we see all these are conditional probabilities. All of them say the same things, but they're conditioned based on whether you're dealing with a millennial, a Gen X, or a baby boomer mature person. So that's the tree diagram. Part B of this question, we're going to use the same exact tree diagram, says find the probability that the person reads more ebooks than print books. So what's the overall probability that we end up reading more ebooks than print books? And that's just not, not conditioned upon like any of these. So it's not given anything, just what's the overall probability. All right, so to do this, this could be done more easily if they didn't split it up like they did. But we have a bunch of different possibilities. We could randomly get a millennial that reads more, right? And so if we multiply this, we are actually multiplying down the branches of the tree. We're multiplying conditional probabilities. This would be the probability of A times the probability of B given A, for example, if we're doing it. So the probability that you get a millennial and that they read more ebooks, we can multiply those two numbers. Then we can multiply these two numbers to figure out what's the probability to get this type of person, this type of person, and this type of person. And so that math ends up looking like this. So ultimately, the probability that they read more ebooks is all these four categories here at the end, and we can multiply that out, and this would be our total number of millennials. So 6.8, and this is of millennials. This is the total number that are millennial and read ebooks. So it's that 6.8%. And then we have our purple category here for our Gen Xers and our red baby boomers and our blue mature. And so those probabilities all add up, and that gives us, these four outcomes together give us a 20.98, or about a 21% chance overall that the individual reads is more likely to read ebooks. So it would be nice if our study just gave that information right away. They actually could have if they ignored it, but that's just not what we had. So because we had all those different probabilities, we could figure out the overall probability that way. And so what you can do with these tree diagrams is you can figure out specific outcomes at the end of these branches by just multiplying down the branches of the tree. And it's basically, you're following that general multiplication rule. You're multiplying by conditionals. So the problem can get a little more complex still. Suppose that a chosen person reads more ebooks than print books. What is the probability that he or she is a millennial? So given that they're one of those 20.98%, given that they read more ebooks, what's the probability that they're a millennial? And so we're going to solve that this way. We have that 20.98% is our denominator. The numerator for this is the millennial and reads ebooks. This 0.34 times 0.2. If we rewind here, it's the green category, the 6.8%. So 0.34 times 0.2. That's the percent that we're actually interested in. Out of our people that read more ebooks, out of our 29%, 6% or 7%-ish of them are millennials. And so ultimately, so it's like 0.06 out of the 0.20, we end up with 32% chance. So given that they are an ebook reader, there's a 32% chance that they are a millennial. And so that's kind of a little bit reversing things. All right, then we have multiplication rule for independent events. So we have our general multiplication rule, which is the probability of like A times the probability of B given A, or vice versa. What we have is if we're independent, the probability of B given A is the exact same thing as the probability of B. It doesn't matter that A happened. So we can simplify the general multiplication rule as follows. So if this is our general multiplication rule, probability of A times the probability of B given A, if we're dealing with independent, then we can just multiply by the probability of B. So probability of A times probability of B. So if A and B are independent events, then the probability that A and B both occur is the probability of A times the probability of B. But that only applies when you're dealing with independent events. So for instance, if I want to know what's the probability that I flip a coin and get heads and then roll a die and get a 6 or something like that, I could multiply those two probabilities. I don't need to do, like, if I flip the coin and it's a 50-50 chance, so 1/2, and then I roll the die, it's 1/6. The die doesn't care what happened. It didn't matter whether it was heads or tails. Those two results are independent, right? When we are rolling dice multiple times or flipping coins multiple times, each flip is independent of previous flips. It doesn't care. Now, be careful, like if you're drawing cards off of a deck and you're not replacing them, now it actually is dependent, and you need to make sure you think about the conditional. Given that I already drew 4 cards or whatever, what's the probability I get this or that? But things like coin flips and die rolls and spinners and things, those are generally independent events, and so we don't have to think about this conditional. We can just multiply out probabilities. So here's an example problem. Many people who visit clinics to be tested for HIV, the virus that causes AIDS, don't come back to learn their test results. Clinics now use rapid HIV tests. They give the results while the client waits. In a clinic in Malawi, I don't know how you say that, for example, use of rapid tests increase for the percentage of clients who learned that their tests who learned their test results from 69% to over 99%. The trade-off for fast results is that the rapid tests are less accurate and slower than slower laboratory tests. Applied to people who have no HIV antibodies, one rapid test has a probability of being about 0.004 of producing a false positive. So this is one thing that we should know about now, is that when you take any sort of medical test, there's usually this chance of a false positive, just happens to test positive, even though it's not that. So we have this. So if they don't have HIV, they have that false positive rate. So that's falsely indicating that antibodies are present. If a clinic tests 200 randomly select people who are free of HIV antibodies, what is the probability that at least one false positive will occur? Assume that the test results for different individuals are independent. So they're going to test for 200 people. So we could figure out, the one way of doing this is we could try and, we could try and figure out, all the different ways for each individual and multiply it out. But actually, the best way of doing this type of situation is if I want no false positives, so we can do just a multiplier here. So, so the probability that all 200 tests are negative. And so we would multiply 0.996. That would be a negative test. So there's this 0.004 probability of a false positive. So there's a 99.6% chance that they'll test negative. And then we'll multiply by the next individual and the next individual and the next individual. Well, rather than doing all the multiplication, we realize that's what exponents are for. We can actually just do 0.996 to the 200th power. We would have 200 of these multiplied out. And so ultimately that probability that we get no false positives is actually only 44.86%. It's kind of a toss-up. And so that means actually the probability that you would get a false positive out of 200, so that you have at least one false positive, is 1 minus that, or 0.5514. There's a 55% chance you would get at least one. And so that's an important thing to realize when you're doing some of these problems, that the at least one is the best way to do that oftentimes is to figure out the probability of none and then do 1 minus that, because at least one is the complement of none. So kind of use some of those strategies, different probability rules when you encounter these problems.